All right, so now that we are finished with example 1, we're done with example 1 completely. But allow me to still retain the problem that we saw in example 1 so that I can develop some other ideas so that we can keep convincing ourselves that how base E is the winner. Okay, and so now throughout a lot of my, throughout the entire lecture time so far, I've been particularly emphasizing the fact that this problem here, I use that term, I emphasize on that term, the default time period. Whereas I did not particularly focus on the term whether it's annually or monthly or bi-weekly or whatever. Okay, so the idea, generally speaking, is any of these rates here that's given in a financial math problem, and you have also seen a little bit of those in those other the population growth problem or the exponential decay problem I introduced prior to getting to these financial math problems right here. So these rates are always associated with some kind of default time period right here, and so being annually or being annual or being monthly or being whatever, it's just basically a default time period that's associated with the rates given. So that's one thing I want to make it clear, and I want to emphasize I want to emphasize in your understanding that there's always a default time period. I mean, there will be a couple times here and there throughout our problem solving that we may have to assume some default time period, but usually, or big high percentage of time right there, large percentage of time, it's given. Okay, but now after taking that understanding, then allow me to take this problem from example 1 that we've done and head into another direction right here. So now this rate right here, this rate is, yes, right from the problem of example 1 is given, it's the interest rate. It's the interest rate at calculated at being 3% annually. So annual is the default time period. And then ultimately we came to, part C of the example 1, we already came to the following function that meets our continuous compounding the requirements here. So if we're compounding our interest continuously, okay, if we're doing that, then we have seen throughout example 1 in part C particularly that the quantity at any time t years. So just like that, once we have set out a default time period, then that amount of time period is how your time variable is being measured in terms of. So if the problem refers to default time periods being in days, then t is the future amount in t days. Okay, the future quantity amount in t days. Or if the default time period is in week, then the t here is in how many weeks, and then 1.5 weeks means a week and 3.5 days. Okay, and that's the idea right there. So now for this particular problem, again, the default time is in years. So Q of t is the quantity of the quantity or the future value in t years. Okay, the value in t years. But then as our interest is compounded continuously, then we came to that function being 3,000. So as a reminder, that was our initial amount. And we're going to multiply with base e as an exponential function, base e to the 0.03 t. Okay, base e to the 0.03 t. So now you have seen this before as well, but now I really want to emphasize this. I really want to emphasize that, and then take from this fact, I'm going to take that on and lead into a further understanding right here. But notice that the coefficient in front of our t in this exponential function, if you pay attention right here, because this part is needless to say, it's always there. That initial amount is always there. But now look, if we're looking at the anatomy of this, e to the this exponential function base e right here, then it has, aside from the variable in the exponential component, aside from that variable, it has a coefficient. And so that coefficient here is exactly the value that we found in this given rate, like that. Okay, that we found in that given rate. However, let's now do the real thing I want to head out now is that let's do a comparison. Let's just make a comparison right here. All right. So now on this board, let me make the following comparison. Now, if it was just simply compounded, if the interest is compounded or is calculated annually, okay, then our function, we've seen this earlier, or in case we haven't seen this in the actual example itself, then we can easily come up with that by, in t years, we're looking at 3,000 multiplied with, at least the discussion prior to getting to the financial math here can lead us there. 1 plus 0.03 to the t. This is how we just, if it's compounded annually right here. And so the function itself becomes 3,000 times 1.03 t. Okay? And so the way how I arrive at this factor right here that's raised to the t is exactly the same as how I was explaining about that problem number 3 prior to getting into this specific area about, talking about the financial math problems. Okay? And so now, but now if we're comparing with the version where we compound, where we're having our interest compounded continuously, okay, then Q of t is 3,000 e to the 0.03 t. Okay, and we also talked about right at the end of our discussion on, particularly problem number 3, because this example 1 right here is very similar to problem 3 that I brought up earlier. So right at the end of problem 3 that I highlighted that going with continuously compounded, going with a plan where your interest is compounded continuously, that plan will give the highest yield, okay, the highest yield. So now let's compare the following. Okay, so now, needless to say, in this year, in this plan here where interest is compounded annually, where the interest is compounded annually, then think about at the initial time Q0, then that's 3,000 for the initial amount. But then in 1 year, so now Q1, I'm talking about precisely 1 year later. Precisely 1 year later, we're looking at, according to this function, it's 3,000, okay, times 1.03, okay, and then the calculation shows, all right, so just now I graphed a value and did a calculation there on my computer station like that, but the calculation here shows, so I'm talking about exactly 1 year after the initial amount. Then we end up with a future value being $3,090. $3,090. So indeed, so now that's the initial amount. That's the amount 1 year later. So after that, showing the calculation allow me to write them a little bit together right here so that I can make some more space. So initial amount is 3,000. Okay. 1 year later is 3,090. So now in 1 year jump, we produced the interest produced with the interest earned right there. We produce that extra $90 right here. So let's do the following math right here. Okay. So let's do the following math. I'm going to go with Q1. I'm taking the difference between Q1 and the initial amount. Or let's now use a formal symbol, Q1 minus Q0. So 2 consecutive periods I mean 2 consecutive time points of one period. That's to be precise, 2 consecutive time points. Okay, that's the way how I see it. I'm gonna take here I'm using time 0 and time 1 year away, but basically it's 2 consecutive time points of the default time periods. In this problem, the default time period is 1 year. So here I'm taking, you know, the quantity in 1 year later after the initial time. So I'm taking that difference and I'm dividing by the actual amount at the initial time. So doing this, I'm going to come up with the following. So it comes out easily as 3,090 minus 3,000 initially, and we divide it by 3,000. That calculation. And so with this, it gives me a percentage. It gives me a percentage. All right, and so now with this calculation, allow me to erase that and write the final calculation. So the final calculation here is a 90 out of 3,000, okay, which is really a 3%. So this is no doubt about it, because the problem gave us right from the beginning. The problem told us, hey, you know, we awarding you, we're rewarding you, we're paying you from the bank. I'm talking about from the bank. Speaking to from the bank, talking to an investor that we're gonna award you or we're gonna pay you 3% annually. So it's the rule that the bank set out. It's a rule that the bank set out. So it makes sense that after we take this difference, right here, that's to find out how much we produced in one default time period by taking that difference generally, and then setting that difference as to and understood as the amount produced within one default time period and over the previous time point right here, then it falls perfectly into this amount. It's the interest rate that's offered. Okay, so this one here is just no doubt about it. But now if we're looking into this version and notice this problem I'm looking at here is compounded annually, which is exactly, you know, going equally with that default time period indicated in the problem. But now there were times that we needed, you know, from whatever the information here, the bank offered us, you know, interest rates being 3% annually or 3% in a default time period. But now we want to go with we decided to go with compounded continuously, okay, with the continuous compounding plan right there. So let's do the similar thing. So now with this, I am going to do the following again. At time 0, when we're just starting out, the initial amount is 3,000, no doubt about it. Okay, but now when it comes to 1 year away, but the idea now, so you can go with Q2 and then here it's Q3. But the idea again is we pick any 2 time points from one default time period. So here our default time period is a year. Again, as a reminder, for this particular problem from example 1, the default time period is a year. And so that's why I go for to save us some efforts in calculation, I go directly from the initial amount to, you know, the amount that happens 1 year later. But more generally speaking, because there will be times later on we will deal with problems that are less information given. Okay, so here it's quite ready for any one of us, so we can save some efforts by just doing time 0, right, and then time, you know, exactly 1 year later, and 1 year is the default time period, and other time if it's if the default time period is 1 month, then we're talking about initial time, and then how much it's produced, how much interest produced and accumulated from in 1 month later. Okay, and so that's the idea. So in that way, I'm calculating Q1 1 year later. That gives me, but according to this function, it gives me 3,000 times e to the 0.03. E to the 0.03. So let's do a quick calculation here. All right, and of course we have to do some rounding when it comes to the money, when it comes to the financial math right here, and it deals directly with the money. So we have to round to 2 decimal places because it's the way how money runs right there. So this calculation will come out being $3,091. $3,091, not $3,090 like in this plan we've had earlier, and 36 cents. Okay, and 36 cents. So this is our future value in 1 year away from that previous point right there. So basically, if we think about how much money was yield, okay, how much money has been yield, then we're going with Q1, Q at 1 minus Q of 0, and we're dividing that by Q of 0 again. Because taking this difference is indicating for me how much money we have produced for ourselves. Okay, how much money has yielded. Okay, and then we're going to divide that by, because how much is yield on top of what happens, on top of what was there in the previous time point, in the previous time period. And so that's why now we're dividing that by, it makes sense when we measure that yielded amount over the amount that was there from the last period. And so now it gives me, so it's really 91.36 cents, $91.36. We put in that over 3,000. Okay, so let's look at this number right here. So it gives me really indeed, right. All right, so my calculation showed .03045, and a lot longer. Okay, so now that's equivalent to about a 3.045 and a lot longer, but percent. All right, so let's observe a little more carefully here. So wait a minute, I thought the bank was offering, so what this says here right now with this number, the jump here is a year, okay? The default time period is a year. So the way how I interpret this percentage right here is that every year we're gonna produce for ourselves, about 3.04545% from the previous year. Every year we're going to produce for ourselves about 3.04545 and a lot longer percent from the previous year. But it does happen to be a little bit higher than what's stated. It does look to be a little higher than what's stated here. I mean, I'm not talking about so we round it because it's so close to 3%, so we round it down to 3%. Nope, that's not the case. I'm now talking about, yes, this is what's stated from the bank. Like in the next year, it should only produce for us exactly 3%. I'm talking about this statement here is if it was like that, it should be exactly 3% produced for the next year right there. Okay, and then because it's 3% annually, it's the interest rate. But now think about what happened just now. If we went with the continuously compounding plan right there, okay, then it's actually produce more the percentage of yield right here. See, so this is called the percentage yield right here. The percentage of yield is indeed a little bit higher, and in some other problem it could be noticeably higher than what's stated in the beginning of the problem. All right, so keep in mind the idea that what's stated in the problem usually comes with the the default time periods. But now as we are doing more the sub periods, we are doing more periods of compounding in each time period right there, in each of the default time periods. Then we actually gonna we're gonna come up with something that's slightly higher. Okay, so what I want to point out now is that this thing here came out from observation. So we observe what's happening. So the bank stated like 3%, but now indeed, if we went with this plan right here, we earned even more. We got even a slightly higher percentage yield right there. Okay, percentage yield. But then in the end, yes, I just now call it a percentage yield, but it's just another interest rate. It's just how much we earned, how much the bank actually reward us or pay us at the end of each period right there. So here I choose time 0 and time 1. But basically, again, it's 2 time points of one particular default time period right here. And so for each default time period, the real observed, the actual percentage that the bank paid us is 3.045. I mean, if we round here, then it makes sense to round to 30.45. Still higher than just exactly 3%. It earns more money. Obviously, you know, with this plan, it only yielded for us $90, whereas here it yielded for us 91.36 cents. So it's even a little extra like that. All right, as the amount of yielding, and so that's why this number here is called the percentage yield. Okay, so the percentage yield here in the default time here is just 3%, but now so the idea now is that if we compounding more frequently, if we're calculating interest more frequently than what's stated with the default time periods, then of course we're gonna expect some actual. We're gonna in reality, that's basically the idea. In reality, the actual yielded percentage is higher, or the actual percentage yield is higher than what's stated in the problem. And it's always like that. It's always like that in any of the financial math problem. Okay, and so let me even point out: does it only happen in the plan where we're compounding or we're calculating interest continuously? So what about aside from continuously? Let's go with the monthly, for example. Okay. So now allow me to quickly erase this, because I still want to do a comparison with this 3%. All right, so if we're going to compound it monthly, let's see what's happening. If we're compounding monthly, right, then the quantity, the amount in the bank for some t years later is going to be 3,000, the initial amount, times 1 plus, and you have seen this work right here. At least, if not directly in example 1, then you must have seen that throughout my discussion on the problem number 3 that I brought up earlier, because the work is extremely similar. So 1 plus, now our interest rate stated in the problem now, so I call it the interest rate stated in the problem annually is a 0.03, but now we're going with monthly compounding period right there. So we're going to divide by 12 because n equals 12. There are 12 compounding periods per year, and then now 12t. Okay, so that's our function right there. And so now let me quickly, and so that means I can calculate Q1 as following. So 1 year away from the initial time. Let me quickly swing over to my calculator at the computer station here. All right, so right for my calculation, 1 year later in this function right there, then the amount calculated as $3,091 and 24 cents. $3,091 and 24 cents. Okay, but then if we're doing that math again, very similar. I'm gonna go, because we want to calculate the percentage yield. Okay, that's the key I start bringing in right there. So Q1 minus Q0 divided by Q0. This is 3,000, that's 3,000, but this is 3,091.24. Okay, $3,091.24. And then so doing that, we're looking at So for my calculation, I've had 0.03, 04, 159, and a lot longer. All right. So in percentage, because remember again, this is how I find what's so-called percentage yield. How much actually yielded? How much has actually been yielded? Okay, over 1 year period of time. I mean, I went with time 0 and time 1 year, but you can also go with time being 1 year and time being 2 years. The point is again 2 time points of one default time period. Okay, so that difference divided by the time point exactly 1 year before, I came up with this calculation. But then in percentage, it's 3.04, 159, and a lot longer percent. So it's still higher than this rate. And this rate, again, is stated in the problem. This interest rate is stated in the problem. The bank is telling us, hey, we're going to pay you 3% per year. Okay, but then if we're going with if any of one of us being the investors, okay, going with the plan where we're calculating our interest monthly, we're compounding our interest monthly, then indeed we earn better. We earn better than what the bank offer. Okay, we earn better than the actual earning for us, the actual yielding for us, the actual yield for us here is better than this percentage. The percent here is 3.04159%. Hey, it's money, so the higher the better. Okay, and so now clearly we still keep circulating around the idea that as we compounding the interest more often, more frequently in one period, within one the default time period, okay, then we definitely will produce a lot more. And because we produce more, either we go with monthly or quarterly or continuously. Okay, anytime that we are compounding or calculating interest, the more often than the default one right here, then just staying with the default time period right there, then we definitely will earn more. And so the percentage yield right here, this is called the percentage yield. Okay, so now I've done 2 problems to compare with the beginning one. So now let me erase this, and we're going to formalize some terms right here. All right, so for compounded annually, I use the term the percentage yield. If we went with that plan right there, compounding our interest annually, then the percentage yield is exactly the same as the interest rate stated in the problem. It's 3%. Okay, but then we also investigated if we compounded our interest monthly. Okay, so I show that calculation, and now we call that calculation the percentage yield. The percentage yield is being 3 point, and just now I erased that 3.0 for 159, and a lot longer percent. So the percentage yield keep getting higher and higher as we increase our number of compounding periods per default time period. Okay, and so monthly means in 1 year we are compounding our interest 12 times in a year, and so that's why that's what resulted in this percentage yield being higher than the percentage yield that's going 3%. So you see, and here the number of compounding period is exactly equal with the default, just being once in every default time period. So this percentage yield stays exactly the same with whatever stated in the problem. But now as we keep increasing the number of compounding periods in each of the default time periods, then we're gonna keep expecting higher and higher the percentage yield right here. And so that's why now when we saw earlier, when it comes to compounding our interest continuously, I only need to show a couple plans here. when we compounded our interest continuously, then we came to percentage yield. We came to percentage yield being 3.04545 and a lot longer percent. It's still, and it's even better than that. Okay, and it's even better than that. Okay, so now in this particular problem right here, the interest rate stated in the problem at the beginning was associated with the default time period to be annual. Okay, and so this is the reason why. And admittedly, in a lot of problems out there, a lot of the real life problems when it comes to financial math, yes, a big amount of time, a big percentage of time that interest rate is given very commonly in default time periods being yearly, being annually, admittedly. But there are still exceptions out there. There are the short-term loans where interest rate is stated in terms of per month or per week. It happens that way too. So that's why I want you to be more open and be more aware about what's decided as a default time period, rather than tying your mind down to only it has to be annually. It has to be annually. Okay. So there's generally there's always a default time period. But now in this particular problem here, then the default time period is being annual, being yearly. So in that way right here, yes, this percentage yield right here is called, we can call that the annual percentage yield. Annual percentage yield. And this is annual percentage yield. And this is also the annual percentage yield. Or for short, it's the APY that a lot of time financial experts out there is referring to. This is the APY right there. Okay? So what exactly is a percentage yield right here? And in this particular problem, it's the APY. In this particular problem, it's the annual percentage yield, because we call it annual. See, it's annual because in the beginning, the beginning interest rate, the interest rate stated in the beginning of the problem was expressed in terms of the default time period being yearly, per year. Okay, per year, and that's why this is called annual percentage yield. Okay, and so for now in this particular problem, then what do we call in that way right here? So annual percentage yield, or the percentage yield, is basically just the actual observed. It's the actual observed after the effect of compounding your interest more frequently than just by each time period right there. Okay, so in this default time period, it's a year, and so we only see when the default time period being a year, then APY for annually is exactly the same as whatever is stated. But now when it comes to more often, when it comes to more frequently compounding your interest in one default period, then the APY here, the actual observed percentage yield, a lot of time is always higher, okay, higher than the one stated in the problem right there. Okay, and so now so for this problem here, this value that's always stated in the problem, which is a lot of time that's how it runs, this is called annual percentage. Well, because it's given in percentage. So annual percentage rate. All right. And so at this point, I have to make it clear. A lot of times, when anyone is being a beginner in financial math, there's a high chance that that you misunderstand between the two, that you mix up between the two, that's because annual percentage rate is referred as an APR. Okay, so a lot of times these two, the APR and APY, are mixed up together or confused together. So it's all about when you actually compounding, as frequently as just how they as just frequently as, you know, only one time in each of your default time periods, only one time in each of your default periods, then the APY will exactly equal APR. But now see, in these cases, when you are compounding your interest more frequently than what's stated in the APR right there, because the default time period here is 1 year. So when you're compounding your interest more frequently, then APY is always greater. APY is even greater than APR here. All right, APY is even greater APR. Okay, so that's what happened, and at least I show how to calculate the percentage yield here. And for this particular problem, it's the annual percentage yield. Basically, after the effect, because see, the reason it came to higher API, I mean, the reason it came to higher, you know, it came to APY being higher than APR in this problem simply because there was the effect. There was the effect of compounding your interest more often, more frequently than going with just the usual plan like this, just once per time period, once per time period, okay, once per default time period, once per default time period. See, this right here focus on the concept that only compounded once, okay, per default time period. All right. So for anyone who's intending to do some financial math like that in your life, either at this time point or some future time point, pay good attention to this kind of thing right here. All right, and then now starting with compounded monthly or compounded continuously or compounded daily or anything like that, we are compounding more frequently than once per time default time period. Okay, so starting at this point right here, see these two problems down here, we are compounded. We're compounded more frequently. All right, and because there's that idea about we're compounding more frequently than just once per default time period right there. And that's why there's that effect. There's that effect on that came out consequently from compounding more frequently than once per default time period. And that's why it produced the idea. It produced the fact that it consequently led to the fact that the APY became higher than the APR right there. And once again, APY in this particular problem is referred as annual percentage yield. It's used, annual is used often enough so that it becomes a term, but more generally, it's just the percentage yield, the actual percentage yield that we observed per month or per year, per whatever the default time. The default time here is a yearly for this problem, but in other problems, if the default time period is a month, then it's going to call the monthly percentage yield or monthly percentage yield here, MPY. Sometimes I do see that term MPY sometimes. Okay, or weekly percentage yield, but basically it's the actual observed, it's the actual that we can observe, the actual percentage we observe of how much our value has grown, okay, over that one default period of time. Okay, and so that's the idea right there. So this rate right here is for this problem, it's called the APY, but more generally it's some kind of observed, some kind of actual or observed the rate of yield, okay, rate of yielding after the effect of compounding the more frequently than once per default time period. Okay, and so now we start getting into that idea right there a little bit. All right, so now allow me to quickly come up with another little problem right there. Okay, so you see I can go with interest rate, and this is I still keep some data from example 1, but allow me to come up with a completely different scenario. Okay, so let's say we have an initial amount. We have an initial amount still being $3,000. All right. And then, but think about this. A lot of times we have to borrow, a lot of times somebody lend us a short-term loan that only lasts for a few months. There are terms like that. That's why it's called short-term loans. Instead of, like a home mortgage, the loan lasts for at least 15 years or even longer than that in years. But short-term loans mean the kind of loans where we have to, finish paying off in a certain short amount of time, like usually less than a year. And so likely those kind of investment where the bank is investing on us right there, then those kind of investment is the interest rate is likely to be calculated in terms of the months. Okay, so the interest rate. So now the same amount of initial amount right here, but allow me to use interest rate being still 3%, but I'm gonna how about change that to 3% monthly. All right, the interest rate is 3% monthly, and then that's all the information we have right there. And so yes, monthly in this problem right here. This is the default. This is the default time periods. So each default time period is 1 month apart. Each default time period is more 1 month apart. So even we're stepping outside, we're stepping out of the world of annual interest or annual percentage yield. But if now we set our default time period to something different than annually, we can still do the similar thing. Okay, so now if we really are going to compound our interest monthly, so now notice I always tend to start out with the plan that's going once. This is once per default periods. Okay. Time period. The default time period here is 1 month. So if we calculating compound, now at this point compounding the interest means we're calculating the interest, okay, monthly. So if we're calculating interest monthly, or basically more generally speaking, once per default time period, then yes, the future quantity, so in some t months later, in some t months. So yes, t is the time variable, but now in months. Makes perfect sense that way. Okay, so now in t months, then we're looking at 3,000 times 1 plus 0.03 again. Nothing surprising to the t. So this is just like the problem I brought up on the other board right there. Okay, and so now the actual yield right here. But now see, so py here is percentage yield, but we cannot call that APY anymore. We cannot call that annual percentage yield anymore, because this is really the monthly. This rate right here is a monthly yield right here. See, so maybe we can use that MPY. I have seen that term earlier. I mean, I've seen that term as I read some articles here and there. Even though, admittedly, it's not as commonly used as APY. But again, so if we strictly stay with calculating interest once per default time period, then the observed the percentage yield right here, the observed percentage yield is exactly needless to calculate. Is exactly 3%. In every jump, in every equal jump of 1 month, 1 month, and 1 month, the money we're gonna earn exactly 3% from whatever the preceding month. That's what it is. Okay, and so in this case, MPY equals, so now guess what? In this case right here, where the default time period is in month, then we can call this, we can also call this the MPR, monthly percentage rate. Monthly percentage rate. Okay, so we can call that number, where that value, that percentage, that interest rate here, as monthly percentage. All right, monthly percentage rate. And that's why I used that term MPR earlier. Yes, admittedly, it's not as commonly seen as APR out there, but it does, you know, it does pop out here and there over, you know, a couple of articles somewhere here and there that I've read. Okay, and so there's MPR, there's MPY, but the idea, see, it's all about you. So you don't need to get yourself too tied down to APR or MPR or APY or MPY, but the idea now is that there's a default percentage rate right here. So here the default time period is being month, so it's monthly percentage rate. But it's a default percentage rate right there. And then this is the percentage yield, the actual how much we observe has been yielded, how much has been produced throughout that default time period right there. But now, strictly, if we stay with that plan where we're calculating or we're compounding interest, okay, where we're compounding our interest monthly, in this case, more generally once per default time period, then I'm looking at the MPY here, or the percentage yield for that, for each default time period being exactly 3%. So MPY in this case equals. This is equals to exactly the MPR. Okay, but now let's change plan. Again, default time period for this scenario is 3% monthly. The default time period here is monthly, every month. So we can go with a plan where we're compounding our interest, okay, or calculating our interest daily. All right, so let's assume that there, of course, some month there's 31 days, some month there's 30 days. And that is the reason why, you know, there are not too many times you're seeing, you know, interest rate being written in terms of the days, right there. I mean, in terms of monthly, right there. Because when people need to compound, when people need to calculate the interest in daily basis, right there, then it's a little hard to do the division, because are we dividing by 31 or are we dividing by 30? Okay, because some months it's 31 days and some months it's 30 days. So, and even some months there are only 28 days. Okay, and so that's the reason why a greater amount of time, a greater number of times out there, the banks offer those interest rates measured in default time periods being yearly, because, you know, see, anytime you set yourself in a time frame of 1 year, then there's no doubt about it, 12 months a year. So it's easy to break it down to monthly plan, or, you know, once you set out with an interest rate being, you know, the yearly interest rate at start, then you know, if we need to go, if anyone desire to go with the daily plan for compounding the interest, then it's 365. It's one uniform number right there. We don't have to worry about debating between is it 30 days a month or 31 days a month. That's the reason why. So now in this problem, since I purposely put myself in this situation, let's just assume only in this problem, each month there's only 30 days. I'm only assuming, I mean, I only created that scenario to stay consistent with this problem, that's all. So now compounded the interest, the interest daily right here, then I'm looking at any month, in any T months right here. 3,000 initially came out, and we go with 1 plus 0.03, and I'm dividing by 30, and then raising that by 30t as the power. This is an exponential function. Okay, and so now I am going to, and then once we've had that function right here, then yes, we can go ahead and calculate our monthly percentage yield again. See, the idea now is that it's the actual observed percentage yield, the actual percentage yield per default time period. But now when our plan already went more often. So now let's highlight that. All right, so more frequently, okay? More frequently than once, okay? More frequently than once per default time period. That's the idea. Okay, more frequently. How more frequently? 30 times a month. 30 times in one default time period. Whereas here it's just only once per default time period. A lot more frequently. Okay, so in that case, now do expect that there will be some effects. There will be some effects that will cause some effect on our final yielding in each default time period jump right there. Okay, and so now at this case right here, I am going to calculate I'm going to go ahead and calculate my MPY. I'm going to go ahead and calculate my MPY right here. So MPY again, now I'm going to go with the amount. I'm going to go with the amount in 1 month later minus the initial amount Q0. Okay, and I'm dividing that by Q0. Right after this, I'm going to swing over to the calculator at the computer station to grab a value, and then once I come back here, I'm going to have to erase this setup right here and write down the actual percentage yield right there. Okay. All right. So I figured that it should also be better if I show some of my secrets of the calculation here using the decimals to help me speed up the calculating process right here. But see, this is almost the almost complete function of our here currently. So now all I have to do is put a 30 here for 30 compounding 30 days in a month right here. And now I need to multiply this t here in the exponential components by 30. All right. And so now see, this is Q1, the quantity value in 1 year later. So I set up my Q of t function at this function being exactly, this function is being exactly that function Q of t being the 3000 times 1 plus 0.03 over 30 and raised to the power 30 t like that. Okay. And then once I've had that, then it's making it a lot easier for me to substitute in t equals 1. This is 1 month later. So this is how much I have yielded in this is how much I will end up with in 1 month after the initial amount. So the initial amount was 3,000. 1 month later, I'm ending up with 3,091 and 32 cents. Okay. But now to find the percentage yield right here, I'm going to set up this ratio just like what I wrote on the board. I'm going to set up this quotient right here. So the quantity after 1 month, subtract the initial quantity, and I'm dividing that by the initial quantity Q0. And this is how much it came out right here. All right, so now I'm going to write down this number right here on the board, and I'm going to have to erase this part here on the board. So in that way, my MPY, my monthly percentage yield right here, is in percentage point, 3.0439, and a lot longer percent. And now, just like the scenario I brought up earlier to explain about the existence of percentage yield, the actual percentage yield right there, then this percentage yield, this monthly percentage yield has already been higher than this. It's already higher than the monthly percentage rate stated in the problem. The problem of this scenario I put up right there. Okay? And so similarly, you can do the same with continuously. You can do the same with continuously compounding. All right, so allow me to also swing over to continuous, even though my board admittedly is getting a little bit busy right here. So how about allow me to erase this line right here? Because we have been through enough with that. So now if we stick with that plan where we are calculating our interest continuously, all right, if that's the case, our function q of t will become the following: 3,000 being the initial amount times base e raised to the power of 0.03. So again, just like that, but so time, it looks exactly like the function we've had back in the other the function we've had back in the earlier demonstration. But notice the time here is going in smaller periods. The default time period here is in months, like that. So if you're using this function on going with t equals years, and it's gonna have, I mean, if you use this function with t intended to calculate it how many years later, then keep in mind time is in months right here. So if you want to think about 1 year, then you substitute a 12 in this function indeed. So a lot of times functions look the same, but it meant differently. All right. So here with this function right here, now I'm going to go ahead and calculate and of course definitely when we're compounding our interest continuously, right, like this, when we're calculating our interest continuously, we are doing a lot more frequently than once per default time period. Needless to say about that. Okay, whether you're compounding your interest daily or continuously, it's all about you're calculating your interest a lot more frequently than once per year. I mean, than once per default time period. That's what it is. Okay, so now in this case right here, let's calculate again. What we need to do is, so for this particular scenario, since we go with monthly as the default time period, so that's why I call it monthly percentage yield. We want to find out what percentage has been produced, what percentage is of the yield, okay, after 1 month. And so now I'm looking at, yes, Q1 minus Q0 and divided by Q0. So that's generally the idea again. All right, that's generally the idea. And so now MPY right here, I'm going to swing over to the calculator at my computer station, and I will share my screen right there again. Okay, I will pop my screen on the computer screen so that you can also see how I did the calculation with decimals actually. Okay, because it's a lot more convenient. So now on decimals, I will actually change this part right here to e to the t. I mean 0.03t. So 3,000 times e to the 0.03t. This is our function when we're calculating our interest continuously. So this value 1 right now means 1 month after continuously compounding. Then we're ending up with a future value in 1 month being 3,091.36. Okay, and now our percentage yield here for each time period is 0.03045545. All right. And so now I'm going to head back to the board, and this is the number, and I'm going to write on the board right there. So on my board, MPY in this case. All right, so MPY was calculated as 3.04545, okay, and a lot longer, but in percent. And so again, it's the actual percentage yield here is higher than the percentage rate that was stated in the beginning of the problem right there. The percentage rate is always referenced directly to the default time period. But now because there's the effect of compounding more frequently than once per default time period. Okay, then in that case, there's that effect that caused the actual percentage of yield right there to become higher. Okay, so the actual percentage of yield here become higher. All right, and so now at this point, anyone learning in this lesson started feeling a headache. I already felt that. It started feeling a headache about. So sometimes it's an APY. Sometimes it's an APY, and because it's annual percentage rate, and then versus the annual. APY for annual percentage yield versus annual percentage rate, okay? And then in some other scenario, we have to keep track of MPY for monthly percentage yield versus MPR monthly percentage rate. I mean, it's well, constantly or permanently speaking or commonly speaking, there's percentage yield versus percentage rate. But keeping track of monthly or annually or daily, it could be a headache sometimes, okay? All right, it could be a headache sometimes, but now we're starting to get to that core understanding that there's a clear version between the percentage rate, the rate right there, and in a default time period, that's the key idea right there, versus the percentage yield in the same default time period. But the percentage yield will keep becoming higher and higher compared to the percentage rate, because there's the effect of more compounding periods being done, a lot more compounding periods being done in one default time period compared to this version right here. All right, and so now in that case, allow me to finally introduce this term right here, this terminology where also a lot of times the financial experts use them, and then once we've learned these terms right here, we can also extend these terms into those kind of the exponential growth outside of financial math problems, because in the end it seems like I've been focusing so much to the financial math problems, but this is where we build our understanding, and then from here on we're going to extend that idea to the other the concept outside of financial math. Okay, and so now at this point there's percentage rate versus the percentage yield right there. Percentage rate versus percentage yield. All right, so yes, just like that, the term I've been showing, there's what's so-called percentage rate, okay, versus percentage yield. So percentage rate is just whatever you have seen in the problem. It's a lot of times I try to avoid giving a formal definition, the formal worded definition of what a percentage rate is. We've seen that right through just whatever that percentage rate or interest rate is stated right in the problem, that and usually comes associated with some kind of default time period. Okay, so one thing we know is it's always associated. Okay, associated with a default, okay, a default time period. Yes, that's one thing we know for sure. So in our problem, see, in problem 3, I brought up in the much earlier part of this lecture, I call that the 7% the interest rate per year. Okay. So that there was an annual percentage rate, and it comes associated with a default time period. Okay, and then in example 1, I talked about the bank pays us 3% annually. So there is our percentage rate again. Okay, and then it came with a default time period associated with a default time period being 1 year default time period again. See, and that's the rate that's usually stated right in the description of the problem. And then just now I erased on the board, the kind of problem where the bank or the loan is charging us an interest of 3% per month. So that percentage rate is that percentage rate comes associated with the default time period in the problem. I just erased it. The default time period was per month. Okay, and so, but then aside from that, there's a what's so-called percentage yield right here. So the percentage yield is the actual, okay, the actual observed. Okay, it's the actual one, and then it's observed. Because we have to finish doing all the compounding in order to observe and come up with this percentage yield right there. Otherwise, and just simply, hey, here you go, here's the percentage rate. What is the percentage yield? Nobody knows naturally. Even if a person who is super brilliant at math, in the thought process, the person still have to go through the calculation and come up. And so that's why I call that it's the actual and observed, because it's an observation that's done after you have calculated the final future value in that time frame, like that, in one default time period. That's the idea. So the percentage yield is really the actual observed amount. Okay. In percentage. Written in percentage. That's yielded in one default time period. That's how I see it. The actual observed amount that's yielded in one default time period. That's why in those problems, and I still have one problem on the board right here. So this is the scenario where 3% interest rate was charged, is paid annually, see, once per default time period for annually. So now APY right here, so percentage yield right here, that is being for compounded monthly, for calculating our interest monthly right here, and that means we're calculating 12 times a year. 12 times, see, that's why it's compounded more frequently than once per default time period right there. And so in that way, you see the actual amount in percentage that was yielded in 1 year right here it's yielded about a 3.04159 from the previous time periods. That's the idea. So that's why, in short, I call it it's the actual observed. So we can only come up with this after we have done the calculation and observed the value. Okay, and so now that's the generalized idea right here. So percentage yield is the actual observed amount that's yielded in one default time period. Okay, but now allow me to use a term that's even more, because I talked earlier about it's starting to get frustrating a little bit. It's starting to become a frustration when we have to keep track of monthly or annually and monthly or annually. That's the part, a lot of time it can also make it frustrating. So see, when it's, it could be annual, it could be monthly, it could be weekly, and it could be quarterly. There are a lot of, so talking about a default time period, it's our choice, it's the bank's choice. We have control over that. Okay, so now once we are seeing that, then see if it's annual percentage rate, then here it has to be equivalent to annual percentage yield. See, that's why it's starting to get frustrating right there. And then here it has to be monthly, equivalently, or weekly. But see, as we keep having, if we can just keep changing our convention like that, and it will become a headache right there. Okay, and so now generally speaking, but one rule of thumb I can see, they have to go side by side. They have to go side by side with whatever is chosen here. If we go with annual, then it has to be annual for the percentage yield. If it's monthly for the percentage rate, then it has to be monthly for the percentage yield. Because see, it's always about at least for the percentage yield, we have a definition right here. It's the actual observed amount that's yielded in one default time period. And I use that term percentage yield. I wrote that term in red ink right there, in red color. All right, and so now to reduce that frustration, yes, to reduce that frustration right here. So now allow me to introduce a better term. It generalizes the idea right there, and we can also use these terms and extend extend these terms into those problems outside of the financial math problems as well. Okay, So percentage rate right here, yes, this term is only used among the financial math and among the financial experts right there. But now among the financial experts, we call, so annual percentage rate or monthly percentage rate or weekly percentage rate, any of those rate that comes stated in a problem, usually, right? We refer to that as a nominal rate. All right, nominal rate, sort of like just a starting out rate, like a base rate, a nominal rate. It could be, see, it could be an annual percentage rate, it could be monthly, it could be weekly. The idea of being a nominal rate is that it's a rate that's associated with that's tied down to a certain default time period. That's why I start introducing this term so long ago, before this point right here. So any nominal rate comes with a default time period. It has to be indicated somehow. Now, there are times where some textbooks are writing the problem a little loosely, where without indicating, they give a time, I mean, they give a nominal rate, but without giving a clear indication of what the default time period is. Then in that case, if it's not given, usually it's usually most commonly it's the annual one. But annual or monthly or weekly, it's all just a convention. But the idea now is that the rate given, it's called a nominal rate. Okay? And then once we have that, then the percentage yield right here, you see, I started using that term. There's the effect of compounding the interest more frequently than once per default time period. There's that effect right there. And then because of that effect, it produce these percentage yields. And so it also depends on what kind of plan you went with. Are you compounding the 12 times in your default time periods, or 30 times in your default time periods? Okay, or continuously within one default time period. It all matters that way. And for that reason, percentage yield here is now generally regarded as what's so-called effective, because there's some effects of those compounding of the interest more frequently. So now we call it, this is the effective rate. A percentage is a rate, okay? And then versus nominal rate. All right, there's effective rate and versus nominal rate. Effective rate versus nominal rate. Okay, but now, technically speaking, so effective rates, you will start seeing effective rate as soon as the instance you change the compound, the number of compounding period to more than once in one default time period already. Okay, that's the idea right there. That's generally the idea. Okay, but then, however, as once we're taking this problem, once we're taking these terms and apply them outside of the financial math, and usually it only matters between continuously compounding, continuously growing, or periodically growing, and we will get to that. Okay, all right. So here's the idea, a little more into the talk about these before we head it out. And so now, back to this part of the board right here. I don't need to, let me erase all of these other plans aside from compounding continuously right here. Okay? What I'm about to explain here is that why does it matter? Why does it matter that we have to make we have to make that clear about where it is to be an effective rate and where it is to be a nominal rate, especially when it comes to comparing between compounding continuously versus compounding once per default time period. Okay. So let me bring back that example 1 right here with the data there. So, but now how about, let me call that, we'll compound it once. Okay. Once per default period. So in that problem, it was example 1, of course. So in that problem, it was annual. Okay, it was annual. And so if that is, then t is in years. Okay, and so if we are doing it that way, then of course the formula that we have seen, the formula that we set up, the function that we set up, the exponential function we set up is 3,000 as initial amount times 1 plus 0.03 to the t. No one can argue about that. Okay, whereas here our formula was eventually I had to erase all of that. So whereas when we compounded our interest continuously, okay, if we're doing that, then our quantity will grow in t years according to the following function: 3,000 times e to the 0.03 t. But so back to what I was pointing out about why does it matter? I mean, why is it important to make a clear distinction between these? So yes, this version here is the I just now used that term, introduced that term. This is the nominal rate, because it's the rate given in the problem. And here, if we're compounding once per default time period, okay, then it goes like that. Okay, and then here's that number right here. Yes, that number is consistent. It's always consistent with the nominal rates. That number I highlighted right there. Okay. Whereas in this, if we are compounding once, that's why I underline that term for me. If we are compounding once per default time period, then that number right there is your nominal rate already. Came from your nominal rate. Okay. But then further, why does it matter? So think about it as an actual impact in your reality. I mean, for financial math, this is completely possible over here. This is completely possible. Now, the bank is the one that decides to pay us when we're investing our money for them. When we're investing our money in their bank, and so the bank is the one in control of. So they set up the rules. So 3% per year, or 5% per year, or 10% per year. That's their control. And because it's a rule that they can set up. And so now if we go with this plan right here, compounding once per year, yes, this is truly how it happens behind the scenes. The computer that they use only trigger up and calculate the interest exactly once per year only. And that means half a year between the way, nope, nothing changed. That's the idea. Think about that. Take a moment to think of what I just said. The bank, they set up that rule so they can hire programmers to write computer programs that the amount you give it to them, you hand it over to them, and after you sign and agree with their interest rate, they're going to pay you. Okay, then once the money is handed over to them, that's your initial amount, 3,000 here, for example. Then they already programmed their computer to know that, hey, today's date, only exactly 1 year later from today, then boom, the new amount will come out with the interest accumulated in. That's the idea. But 6 months from today, nothing. Okay? 11 months from today, still nothing. 11 months and 25 days from today, still nothing. It's only going to generate a new amount exactly 1 year from today, if today is your initial time. That's the idea. Okay? And that's what, and I really want to emphasize that in the world of financial math, it is completely possible that way. So the idea, you can see that we're producing money, but very periodically, nothing in between the time. So here we can only stick with, you know, integer time amount only with this plan right here. And so as I pointed out earlier, nothing in between. See, 6 months from the first day of investment, you still see nothing in your account yet. All right, that's the idea. But now with this plan, if the bank agrees to offer you this plan right here, with that given nominal rate, but if the bank agrees to offer you, since you could be a very loyal customer for years or even generations of your family, and now when you go to the bank, they like you, they love you, they want to offer you this to keep you further as a loyal customer, for example. Okay, then they're going to offer you, hey, we're going to offer you a plan where, yes, this is our nominal rate. This is our nominal rate, but we're going to calculate. This is where we can continuously generate money in your account. Not only every second, every instance between the seconds, you're still going to earn more money. Of course, I mean, those amounts are neglectable, but it's still making more money at every instance of your life from now to a year later. Well, assuming we're still talking about, you know, the default time period here as being a year or whatever. But now compounding continuously, the bank has control over that as well. They can set up calculator, they can set up, they can hire programmers to write their program so that the machine can keep calculating, you know, money continuously, so that at any point, say that 6 months later into your investment term, and you decide to quit, and you just go into the bank, tell them, hey, I want to quit. Well, that's just an ideal situation. No banks want to do business with you like that. Okay, but as a scenario, if 6 months into the investment term, and you walk back to the bank and decide to quit, you still already earn some money already. Unlike this case where I say 6 months into the term, there's still nothing. All right, and so that's the idea about, and that's why, you know, so this function here, the rate, the number there, the coefficient there in front of our t variable, you know, is the one consistent with the nominal rate. But then after doing all the calculation, it will give out an actual effective rate right here. So now, but see, of course, I just brought up that idea about you know, the continuously compounding. But then think about it this way. So now, because we're compounding a lot more frequently than doing the once per default time period, then yes, there will be an effective rate. So this effective rate really was, so the effective rate, okay, effective rate in this problem was, I mean, I already showed that calculation. We can show that calculation again. This is, we can go to simply just Q1 minus Q0 and divide it by Q0. And eventually I will be able to show a better way to calculate effective rate rather than just sticking around with this. Okay? But so Q1 minus Q0 divided by Q0, the effective rate, we calculated this already. So let me once again bring it on screen right there for anyone. This is the calculation for the effective rate. This is our Q of t when we're compounding our interest continuously. And now this is the quantity that has grown to in 1 year later, or one default time period, whatever that is. And now this is the effective rate. So earlier I called this the percentage yield, because if I'm writing that in percentage, it's 3.04545, and now it's a new name. It has a new name. This is called, more generally, it's called an effective rate. This is an effective rate. Okay, and so the effective rate, with this effective rate right here, with that effective rate I shown being 0.03, 045, 45, and a lot longer. Okay, being that effective rate, and clearly it was already higher than the nominal rate. So just like that, like how I was pointing out, APY or MPY is a lot of times higher than APR or MPR, because we come to the compounding more frequently in one default time period than just one time. Okay, and that's the reason why. And then now after I introduced that term about effective rate, I tend to focus on those situations where we are compounding more frequently, already more frequently than the once per default time period. And now particularly I would like to only just focus on comparing, and that's the way how it is. And I'm preparing anyone to also step out of the financial math problem and be ready for the other kinds of exponential growth problem or exponential decay problems out there. So now I particularly focus between compounding continuously and compounding once per default time period. And so this is, I explained there was a jump, and then between the jump right there's nothing in between the default time period. And so now here we do have a lot of calculation during the default time period, and that's how we came up to an actual effective rate being higher. Okay, so that's our effective rate, and here I particularly only need to focus on the two cases here, compounded continuously versus compounded once per default time period. But now, what can we do with this effective rate right here? Allow me to use this board. And so now once we have come to our effective rate, so after the effect of compounding continuously, then we came to the effective rate. So when we use the term effective rate, we just need to be careful in terms of indicating which plan we came from. Is that continuous plan or the compounding monthly plan or whatever? But now specifically, I focused on continuous, compounding continuously right there. Okay, so the effective rate here was indeed, let's call that an R. It's a rate, it's an R, but it's not the ordinary nominal rate anymore. So nominal rates already use the R. So this rate right here, 0.03, back in the problem, this rate is R. So R equals 0.03. So I can't use this R again for a different meaning, slightly different meaning. Because effective rate, and especially when we already agree among each other, instructor and students, that we're currently focused on comparing between continuously compounded, okay, and once per default time period compounding, okay, then this effective rate is definitely higher than that. And so I have to use a subscript E right here. So now if you're reading different textbooks out there on the markets, yes, there are quite a few textbooks using this subscript E right here for effective rate. So it's a rate or effective rate. Okay, and so here we're talking about yearly, so the effective rate here is in terms of year. So now more specifically, annual effective rate. All right. It's simply because our problem, the default time period was in year. Okay, so we pay attention to that. But now this is 0.034545, okay, and a lot longer. And so now, at this point, our money is still growing. I'm talking about now our money is still growing continuously because we already departed. Because we already departed from this plan right here, growing the money only once a year. Growing the money once a year. We already departed from that plan. We stick with this plan. But now I'm talking about if we keep coming back and observe our account. If we keep coming back and observe our account, I'm not talking about the machine producing the amount for us. The machine is still producing the amount for us continuously in this model right here. Okay? So again, I'm talking about we already departed away from this plan where we compound our interest once per default time period. We left that because it's not giving as much money for us as here. Simply that's the reason. And it's not giving us the money as continuously, as frequently as here. That's why we departed from that and we stick with that. But now once we already know that we're currently working with, we're currently letting our money grow continuously. Then this, again, I use that term, this is the observed rate. Yes, now we call it effective rate, but in the end it's the rate where we observe. So think about each year, right after the initial time, each year you look back into your account and you observe it, you monitor it. Each year, if you look back and monitor how much your money has grown, and this is what you observe here, this is what you observe here, and it becomes quite fascinating. Okay, so 3,000 at start. All right, but each year when you come back, you're going to see 1 plus 0.03045, not exactly 1 plus 0.03 any longer, but each year, say today I brought in the amount $3,000. And I go to the bank and I tell them, hey, I want to invest. And then the bank, and I've been a loyal customer for 40 years. So they offer me a plan where it's nominal rate is 3% annual. Okay, that's nominal rates being 3% annual. But now they further offer me that they're gonna calculate interest. They're gonna offer me that my interest will be calculated continuously. So that means it's already, once upon signing that agreement, then it's already a continuous model that the money will continuously grow. But of course, I don't have time to keep swinging back to the bank to log into my bank account, my online bank account every instance of my life just to look at that. Okay, so I can just set for myself a schedule, like say I'm only gonna look into my account once a year. So 1 year from today, it's going to grow this much. Okay? But this is already, see, 1 year from today, after continuously compounding, it's going to grow, the amount is going to grow this much. That's why I'm making it clear that this is what we observed after we know that our plan is going continuously growing the money. And then, so in that way, after 2 years, our money will go like this. 1 plus 0.0304545 square. See, that's after 2 years. Okay, and then after 3 years, our money will grow 3,000 times 1 plus 0.0304545 and longer. 3. That's the idea right there. I mean, the way how I derived this is really analogous, really similar to how I derived that earlier when it was just sticking with the nominal rates. But now with the effective rate, it's just, instead of, looking directly at the e to the 0.03 function right there, e to the 0.03t function, a lot of people refuse to work with that. Okay, and then easier, we can just do something like this. And so, now I'm talking about if we're observing our bank account at some t years later. Okay, at some t year later. So that quantity there, Q of t, will be 3,000 in parentheses, times in parentheses 1 plus 0.03045. Okay. To the t. This is another way to express my continuously growing future value right there. This is another exponential function aside from, see, once the money is growing continuously, technically it was, or theoretically it was 3,000 times e to the 0.03t. Yes, this is no doubt about it. But now I'm talking about, for us here, if we want to observe that, or we sit home and we don't like using this formula. Surprisingly, a lot of people back out using this because, first off, not every calculator has this number. Okay, and it's a very irrational number. We only need we only the more advanced calculator can handle that. Some of the more basic ones, I'm still seeing calculators out there that only offer basic multiplication and basic multiplication and division and plus and subtraction. No fancy power or anything like that. So with out of date calculator like that, then there's no luck for calculating your money yearly with this. And that's why this formula could be better. Maybe 5 decimals, 10 decimals, but it's still completely doable for a lot of people. And so this is really the same function. This is really the same function, but written in a different base. And observe that the different base here. What's in that different base right there? The way how I'm seeing it now is that it's Q of t, and it's the initial amount, just like that. So there's always the initial amount, but then we multiply with the 1 plus the effective rate. 1 plus RE right here to the t power. Okay, and so like I said, this is just a different version of the same function because your money is already in a plan where it's growing continuously. It's growing continuously. So what you have, the reason you ended up with this value right here is simply because it came out from observation. It's your effective rate right there. And so now once we're talking about just simply observing your account, that value came out, as an observation. Okay, as an observed rate right there, then think about if you're sitting home and observing your account growing through your online account, and every year it's easier to calculate your money grow yearly by using this formula instead of jumping right into this, even though they will give you the exact same result. All right, so keep in mind this is not exactly the same as 1 plus 0.03. Somebody blame on the rounding, but it's different intention. The formula we've had earlier, which was still here. This is 1 plus exactly 0.03. This is the nominal rate. So with this formula, it's give you, this is for the bank to calculate the money for us, but which was the plan that we already departed away, because going with this plan we have nothing in between in between a year. Okay, but now with this plan we have money coming out, money being produced in every instance. And now to make it easier for us, simply just to make it easier for us, for any of the investor to sit home, access through their accounts, right, and check for consistency to see if there's anything wrong going on. Is there some instance where the money stopped growing? Then they can check, say, if everything is growing correctly, throughout every instance, then in 1 year later, I can calculate easily that using this function instead of doing this. So Q of 1 here or Q of 1 here will come out exactly the same amount, but it's easier here because I'm using that. I'm re-expressing my function here as in terms of the effective rate. In terms of the effective rate. And so there's only one base raised to the t, whereas using the base e is base e raised to the nominal rate times t. And that's the idea right there. All right. And so now from that reason, so now in that way right here, we can come out with the following. And yes, we're still talking about continuously compounding. We're still talking about our money. Okay, our money is continuously compounding. All right, so now when we're in that case where our money is compounding continuously, then yes, the money at any time, at any month, is Q of 0 times e to the kt. So now if one way we can use that model, just like how I explained earlier, where k now is the nominal rate. Okay, it came from the nominal rate. And then t here is time in the default Okay, time period. Okay, so t is the time. So if the default time period is a monthly, then it's going to be the t here is in years. I mean in months. And if time period, if the default time period is in year, then the t here is in years. That's a standard. Okay, so that's k and that's t, and then q here is of course the initial amount. AMT of mine stands for amount. Okay, q is the initial amount, k is the nominal rate, and then t is the time in the default time. But now aside from that, just now I show how to calculate the effective rate right here. So now if we knew the effective rate, again, I'm only focusing on the compounded continuously right here. We are agree that our money is growing continuously. Then in that case, the same quantity right there can also be modeled by the following function: q sub 0 times 1 plus the effective rate raised to the t. That's another version of that right there. This is another version of that. Okay, they're all continuous model. Again, I make it clear, all continuous model. But this one here gives us a sense about we can calculate that as a prediction more periodically. Okay, more periodically here. But it's still, the money is still growing for half a year here. With this model, we can still figure out how much money half a year. But it's better to use this one when we need to come out with money. We need to come out to check for whether our money is growing correctly in the bank. And I explained that earlier. We don't always have the base E right here. So we're talking about, hey, if we're sitting home and calculating that, stick with a percentage like this. It's easier. Okay, and then so that's periodic. This is continuous function right here. But we're all under that case where our money is growing continuously. There are two different ways we can calculate. One way is to use base E. Okay, but that using the k here is a nominal rate. But then here we don't use the E, but we use the effective rate right here. 1 plus the effective rate. All right, 1 plus the effective rate. So now I purposely put these two side by side right here. They both are continuously, and I explained the reason why there are times we want to use this way of expressing our function to model the amount of money right there, because we want to stay with continuously growing money. Okay, but then we don't want to use base E right there, and then that's why we use this. And so now on this board, all right, so now on this board, here's how I'm seeing it. On one hand, q of t is q sub 0 initial amount times e to the kt, where I explained previously the k here is the nominal rate, okay, and then q is the initial amount, needless to say, and t is the time in the default period, okay, and then and that's that or here, so q of t can be q sub 0 times 1 plus the effective rates raised to the t power. So these are, again, I really want to emphasize that these are to produce the exact same quantity, the exact same future value, where in this case right here, this is the effective rate. Okay, the effective rate for each default time period. All right, for each default time period. And so now let's look at a further impact here, because like I said, these are expectedly to give the exact same quantity, exact same future value. So before I really swing over to do a little math here on the board, allow me to do the following. All right, so now with my decimals right here, and allow me to stay with that scenario earlier where our money is growing continuously now. We agree with that. And this is the initial amount, 3,000. And this was the nominal rates right here, okay? And T here is, let's say T is in years, okay? T is in years. So this is one way of calculating our money, okay? And now let me adjust the graph grid here a little bit. Okay, so I adjust the scaling on my graph a little bit. So this is the graph for Q of T. See, it's a growing, the money is growing, and now the graph is exponential, and it's growing in a one-way bent curve rising up like that. All right, so this is the graph for Q of T. Model in base E right here. So 3,000 times E to the 0.03 T. All right, so now, just now I show how to write the exact same function here. And now let me hide away this graph here, but now let me write some other function. How about let's call it P of T, because it looks different at first. 3,000, and let me change the graph color, and we're not complete yet with the function. Okay, but let's put it here, 3,000 times 1 plus, and the effective rate we've had earlier was 0.0304545, and a lot longer, but for now let's just stay with 7 decimal places. It should be good enough. All right, so now with this right here is the periodic version of the same, tentatively the exact same function, but in a different base to help us observe our amount periodically. Okay, so now let's look at the two graphs right here. And I already had some truncation rounding for the decimals here, otherwise it should be a lot longer than that. Okay, but the 7 decimals is good enough. This is the graph for Q of T, which is the precise version. And now this is the graph for P of T right here. They are, and this is already after I have made some truncation for the rounding right here. Okay, but it still looks identical. All right, and for a very far zoom level, okay, a very far zoom level, the two graphs still look exactly on top of each other. I mean, coincide with each other like that, because they are the same. Because they are the same. All right, and so now after seeing that through the graphical illustration right here, so now once we get back to this, so think about it this way. You saw how the two graphs are exactly the same. The red and the blue earlier was exactly the same. So this consequently, see, because they're all Q of T, just different expression. So in that way, I can now go e to the k t, I mean Q sub 0 times e to the kt. And I can make that equal to Q sub 0 times 1 plus, or I mean 1 plus the effective rate to the t, because these two functions are supposedly exactly equal. And so now we can cancel the Q sub 0 away from both sides because it's a non-zero quantity. Okay, so ending up with e to the kt equals 1 plus, or the effective rate to the t. All right, we didn't get anywhere yet. And again, the whole purpose now, I keep emphasizing the whole purpose now is these are just two different expressions right here, but one expression like this is a little more convenient in case our calculator don't have the base e, and we can, it's a little simpler for a lot of people when they want to monitor, when they want to just sit home and observe their money that's already growing continuously, but they want to observe their money, in a schedule like a yearly, or in a yearly whatever that the time period here is in default. Okay, and so now continuing to my algebra work here a little bit, after canceling out this is what I ended up with. The left hand side e to the kt here is the same as, now it's just a little algebraic understanding, so allow me to explain right here, e to the kt, it's a product between k and t. And so that means I can think of that as e to the k raised to the t power. This is the rule for algebra. That's how I see it. And so now I'm going to substitute this for the left-hand side of my equation right here. So my left-hand side become e to the k, but raised further to the t. All right. So because I was having narrow board space, so I, instead of writing it down as another step, I just erase and write in the next step there. But now, different bases, but we have an equation of same exponents right here. The two equations here, they have different bases, but they are raised to the same exponents t right here, and they are at the moment here they're supposed to be equal according to this equality written here. So that means we come up with the following important result. That means we can take the t roots from both sides, and then it ended up with e to the k is equal 1 plus the effective rate. And this is the relationship that we found. With this relationship, it allows us to easily interchange the base between base E or base the effective rate, base that involves the effective rate. Okay, so we come up with this important effective rate. I mean, this relationship that points out how base E relates with that base where it's involved the effective rate. So this k again is permanently that. Think about the k. Now, if we're still doing financial math, and this k right here came from some nominal rate, that the bank offers. So clearly, in our bank stories right there, we have seen the nominal rates all over. Okay, and then because of that, now when we're compounding continuously, we ended up with the nominal rate stuck in the exponent. And then, like I said, I showed, as I have explained, I show how to calculate the effective rate. It has been a long walk around right there. But now arriving at the effective rate, we have two different forms to express the same model right here. That model is our money that is growing continuously. That's what matters. And I made it clear earlier, we already departed away completely from compounding the interest with just simply the nominal rates per, the compounding interest per one time per period of per default period of time right there. Okay, so once we're calculating this continuously, then we have two different forms to predict our money that's grow in some years later, some months later. Okay, whatever the default time period is. All right. All right, so after seeing some thorough explanations about the difference between the nominal rate and the effective rates, okay, and how a continuous model, a modeling function that models continuously compounding the interest was derived both in terms of the base E and some other base in terms of 1 plus the effective rates raised to the t power. Then now let's do an example to see how this particular skills can be emphasized. Okay, so let me now take you into example 2 right here so that we can explore how important this understanding that we have just now learned can be for us in real life application right here. Okay, so now I'm going to call that example 2. And now after writing down the instructions right here, I'm going to swing over to the computer station and show the data, the worded description, only just the description of the problem in example 2, and then I'm going to get back to the board and write down the various different questions so that we can draw out from this particular problem right here. Okay, so all right, so here we go. This is our worded description for example 2 right here. It's another problem right here, and we only have, so there is no question for this particular problem yet. Okay, so right now everything we have here is simply just the worded description about the situation, about the scenario that we have right here. So at a given annual interest rate, Okay, $4,000 is invested in an account and grows to $8,000 after 15 years of continuous compounding. That's all there is. Really, it looks 3 lines, but really it's just one sentence. So at a given annual interest rate, $4,000 is invested in an account and grows to $8,000 after 15 years of continuous compounding. That is all we have. And so that is the part where, at first it looks worrisome because we don't have as much information. Okay, but now we can quickly sketch down some information. So right on this given information right here, you see this annual interest rate. At this point in our learning, we have learned there were nominal rates. We have learned there is effective rate. And in the way how it was worded here, we may have a little bit of a hard time identifying whether this interest rate, where it's named the annual interest rate, will be whether or not it will be a nominal rate or the effective rate, because both of these can be measured in the same amount of the same default time period right there. So nominal rate can have annual nominal rate or monthly nominal rate, and then when it comes to effective rate, so they'll always be measured in the same equivalent default time period right there. Okay, but how can we tell like that? Surprisingly, for this problem, let me now show you as we walk along with this problem. We don't even need to worry about that particular piece of information. That shouldn't even be anything that we need to worry about. So that information, as far as the information that I highlighted here, now I'm telling you, we don't really have to worry about what kind of rate this is yet, whether it is a nominal rate or it's an effective rate. We will get all of that later, but this one right here is not of a concern right there. What I see here is that $4,000 is invested in an account and grows to $8,000. So $4,000 right here, in the way how I see it, I can see that there as initial amount. So we have initial amount right here. Being $4,000. That's what I know I have. All right. And then here's how another information right here. So according to what we read from the problem right there, then this amount grows to, this amount right here grows to 8,000. So 8,000 is playing in the role of a future value. And so now one more time I'm going to swing back to the worded description right here. But the way how it says, the amount right here, 4,000 that initially invested, grows to 8,000 after 15 years. After 15 years. Okay? So that now is obvious that we have a future value. Okay? Future value. That's being $8,000. Okay? But yes, to make a good note right here, we grow to that amount right here in 15 years. In 15 years. Okay? But now, let me get back to the description a little bit. According to what I explained earlier about this phrase right here, given annual interest rate, we're still at this point unclear whether this interest rate here is a nominal rate or an effective rate. But one thing we know for sure, it does tell us one key right here. It does tell us one clue right here. This is the annual or yearly is going to be our default time period. Okay, so each time period here is 1 year. Okay, this according to that term right there. And so that means now our time variable, so 15 years are here, but T in our problem is the time in years. Okay, that's another understanding that we deserve our attention right there. And so that means now with this future value being 8,000 right here, it means it's 8,000 equivalent to when it's T equals 15. in 15 years or t equals 15. That's how I understand about it. That's when t equals 15. Okay. That's how we can extract information. But at this point, I'm still completely unclear about the rate, whether it is a nominal rate or it's an effective rate. Okay. And now in this particular term right here, when I'm going with the default time period to be annual, then you know the effective rate is also regarded as the annual percentage yield right there. Okay, annual percentage yield. Okay, the APY. But at this point, it's still completely unclear for us about that rate, and the value is also not given. So that's not important. Let's get to that. Okay. So now one more piece of important information to be pointed out right here. Now, so this is our future value after 15 years, but now if we look even further, after 15 years of continuous compounding. Okay? After 15 years of continuous compounding. All right. That means within that, throughout all that years right there, or you know, that means we continuously calculate out the interest throughout the entire time like that, throughout the entire 15 years and even further. Okay, or in another way of saying, in each of the default time periods, we will continuously calculate the interest rate. I mean, we will continuously calculate the interest based on whatever that interest rate that we still don't know at the time yet. Okay, and so from that clue right there, and after all of this information that we wrote down right here, so now allow me to get on the other board and start writing down the first question. I mean, it makes perfect sense about that term. I mean, it's perfectly consistent with that term. It's saying continuous compounding in a sense that now it rings a bell for us that we should use the following model over here. This is just something that rings a bell over here. Q of t is the quantity at time t right here. So the model here should be Q of 0 times e to the kt. Okay. Q of t equals initial amount times e to the kt. So why do I bring up this? Once again, it's back to that explanation because we had that perfect the instruction there. Throughout the whole 15 years, it was things was compounded continuously. Thing was compounded continuously. The interest is compounded continuously, and that's why I'm gonna go for that. It's a perfect place for that. All right, and so now here's my first question. We can call that part A of example 2 right now. So now question A over here. We want to find a function, okay, that models the value, or how about the amount in the account. After t years. This is a general model. Find a function. So in part A, in part A of my problem right here, find a function that models the amount in the account after t years. I mean, it seems like a challenging work right here because we have so little amount of information. But how can we come up with something like this? All right, so here's how I break down, and here's how I can show you that we can just use all that information we have learned up to this point, all of that understanding, we can apply all of that understanding we have learned up to this point into solving this particular question right here. So this is part A from the information we have had, and so we call this example 2. Okay, so as I mentioned earlier, this keyword about continuous compounding. See, after 15 years of continuous compounding right here, that means we have, and in my explanation earlier, we have to stick with this function right here. And that's the easiest choice right there. Q sub 0 times e to the kt. We already know this base is always that famous constant 2.718. So Q sub 0 times e to the kt right here. And then just keep in the back of your mind right here, k in the role of k right here, k is the nominal rate. But unfortunately, we still didn't know what the nominal rate is. The only rate being mentioned here, first of all, it did not have a value. And second, we did not know whether it was the rate described in the problem. We are still unclear whether it's a nominal rate or the effective rate. Okay, we will get to that. But now, one thing for sure from what we've learned prior to getting to this example, then this function, this modeling function right here, this general function form right here, the k in the role of the k in our function here is the nominal rate. If we knew what the nominal rate was, okay, so it's going to be q sub 0 times e to the kt, and then further q sub 0 is the initial amount. That's what q sub 0 is for. All right, so q sub 0 is the initial amount. So now what does, and this is the reason why I chose base e right here, because now recall that right before we got into this example 2 right here, then q of t, we know that our money is growing continuously already. We already knew that by heart, okay, at this point according to the wording, okay. But here, prior to right before we got into this example, then we also learned that even with continuous growth right here for our money, we can still have two different forms of our modeling function. Another form can be q sub 0 times 1 plus the effective rate raised to the t power. But now I chose this simply because we already knew the base e is a finite value 2.718 and a lot longer. We already knew the base, and so less variables for us to find in here. Whereas here we have completely no clue what that effective rate is yet at this moment, and that's the reason why I decided to go with this, and it's actually the only way for now. All right, so now in this way, once I set my goal that I'm going to use this model, okay, I'm going to use this model on using base e right here. Then here's how we can use the information. So on this board right here, initial amount is 4,000. So now if I call my function q of t, then q sub 0 will be this quantity right here. Okay? And now in some 15 years later, this is another important piece of information. In some 15 years later, after the initial amount right here, then the amount grows to 8,000. This is a future value. Okay, but it happens, we reach to that values after 15 years of continuous compounding. 15 years of continuous compounding. So that means, in other words, in 15 years we're going to have the quantity is notationally Q15, Q of 15. That equals 4,000 as our initial amount times e to the k times 15. This is how I'm expressing the quantity, the future value in 15 years. Okay, but on the other hand, we already knew that in 15 years, Q of 15 equals 8,000 because the money grows to 8,000 in 15 years. So again, the whole thought process is as following. The word continuous compounding led me into using this model with base E, and it's the easier one right at start because we already knew the base. And then from further on, according to that information that we know our future value already, and it happens in some given amount of time right there. And so now I'm going to equate these. So that means 8,000 has to equal 4,000 times e to the k times 15 right here. So in other words, so that's just the thought process right here. But as a formal step, we lead to 8,000 equals 4,000 times e to the 15k. All right. And so right now I'm in the role of the instructor showing the steps. So I'm writing down the thought process here. But when you're actually doing on your own work right here, and once you have become mature enough in math, you can indeed skip these two steps right here, because these two steps are more or less just to show the thought process right here. But as far as the formal steps, right from here, q of 15, you can just put 8,000 on the left-hand side of the equation for q of t. And then here, substitute 15 in place of the variable t right there. So we're looking at an equation being 8,000 equals 4,000 times e to the 15k. Now we have an equation that we can solve for k indeed. Because in this entire equation, and in this entire equation, k is the only value that's currently unknown for us. K is the only value that's currently unknown. We know the value for e. We have these values all given, and we know we're looking at particularly that instance where it reached 15 years later. So we just need to find out that k. And so here's the thing. We're about to make some good game-changing moments right here. K is the nominal rate. So once we solve for k, that's the importance of this step right here. Once we solve for k, we will not only know the equation, but we will also know the nominal rates. Because the way how this equation is brought up right here, the way how this formula is brought up, this k value is the nominal rate. All right, so we are now ready to find the nominal rate right here. Okay, so now I can erase this thought process right here and put my equation right up here. So I want 8,000 to equals 4,000 times e to the 15k. All right. And so now I'm going to be solving this equation. The first thing, I'm going to divide both sides by 4,000. All right. And so now I'm ending up with, so 8,000 divided by 4,000 is indeed 2. I mean, anyone seeing the two values, compare the two values, can already see that this problem right here, we double the amount of money, we double the initial amount of money in 15 years. In 15 years of continuous compounding plan like that. Okay, so now 2 equals e to the 15k. I mean, anyone viewing this lesson didn't even need to wait until this step of mine to recognize this kind of equation. Right before I did that step of dividing both sides by 4,000, you could have already recognized that that was an exponential equation. And here in this step, after canceling away the common coefficient 4,000 here on both sides, it ended up with e to the 15k equals 2. We're even further firm that for anyone viewing this lesson, you're even further firm that this is an exponential equation. Or now this is an it's an equation that's in exponential form, simply because the variable we're solving for, the unknown we're solving for, is in the exponential part. All right, so again, let me now bring up a term that you have already been familiar with. This equation here is in exponential form. So now as soon as and this is where this entire lecture is all about, where you see how you can apply your understanding about exponential function, as well as the application of a logarithm that you have learned. So now I have just pointed out about something that you have been familiar with. This is an equation in exponential form. Okay, an equation in exponential form. So now after some learning we have done prior to this particular lecture here, then we can turn this equation into logarithmic form. And particularly it would be convenient to use the log base e, because we already have this written in log base e. All right, and so now, and I don't even have to mention about how we choose the base. It's just naturally like that. So now it's going to be, it means log, natural log base 2, log base e of 2 equals 15k. This is now the logarithmic form. But now after we have successfully put our equation from exponential form to logarithmic form, now we are ready to solve for k, because hey, let's have a look at the right hand side here. The right hand side is simply just a linear expression of the k variable, of our unknown here. So now I'm going to divide both sides by 15. Okay, and this is where I'm ending up with k equals a natural log of 2. This is a known value. This is a value that can easily obtain, can be easily obtained from any standard calculator, and we will divide it by 15. So once we found a value for this, okay, so once we found a value for this is how I'm expressing, because the goal of this problem right here, the goal of this particular function, we want to find the entire equation for this modeling function. Okay, so now we have come up with a k. So now really we're done. Really, we are done. So now finalizing our work right here. I'm going to use this little space here on my the other board right here. But now once we have found the value for k, the nominal rate, q of t is modeled by the following function: 4,000 times e to the natural log of 2 over 15. This is a constant value times t. That's what it is. This is our function that models the growth of the money continuously in our bank, in the bank that we invest. Okay, after some t years. All right, and so in this way right here, it's a little extra to ask from part A. Okay, it's a little extra to ask from part A, but now I'll tell you what, this is our nominal rate. Okay, so as I said, it's extra, so now I can tell you, we can see that k equals natural log of 2 over 15 is the nominal rate. All right, so k equals natural log of 2 over 15 is the nominal rate. And that's the reason why I was saying earlier, when we were still reading the wording description, I was highlighting this phrase, and I said that should not be something that we needed to worry about, because it doesn't matter if it's if this set interest rate to be a nominal rate or an APY, that should not be something important for us right there, because we will have a way to find out, according to the other information, we will have a way to find out what the nominal rate is, and eventually we will be heading out to finding what the percentage yield or the effective rate is. Okay. So that was how we're done with part A of the example. We found a function, and that function was written in base E. All right, and the nominal rate found to be natural log of 2 over 15. All right, so now let's look at part B of the example. All right, so part B, find the effective rate. And of course, this rate here is the annual effective rate. Okay, but in short, it's the effective rate. Or yes, we can also understand this as in this case, it's going annually. So it's APY, annual percentage yield right there. Annual percentage yield. Okay, so now it's just a matter of applying directly that information we have learned just right before we headed into this particular example. We have learned the following important understanding right here. 1 plus the effective rate must equal e to the k. 1 plus the effective rate. So the effective rate is this R sub e right here. That's what it's effective. That's the subscript e, rates, effective rate. So we're not looking for nominal rate. Nominal rate is here. The effective rate is quite different. That's why, so now, but it has a relationship. So 1 plus the effective rate equals e to the nominal rate. We already sort of proven this. We have already proven this sort of, okay, in the earlier work before we headed into this particular example. All right, so now it's just a matter of using this relationship to benefit us right here. We already knew the effective rate. We already knew the nominal rate right here. All right, so now let's see how it can help us to find out the effective rate right here, or the APY. So now we're looking at 1 plus the effective rate to equal e to the, and now our k value was natural log of 2 divided by 15. Natural log of 2 divided by 15. All right, natural log of 2 divided by 15. And so this work I'm sharing a little bit with anyone who love to learn about log, and that's why, as I said earlier in the beginning of this lecture over here, yes, it seems like it's mostly about the application of exponential functions, but there will always be a step here and there that we need to bring in the logarithm understanding, okay, because logarithm and exponential functions are so tightly related. Okay, so here I see logarithm, natural log of 2 over 15, and e to the natural log of 2 over 15. So just a little side work right here, e to the natural log of 15, natural log of 2 over 15, I can see this as e to the natural log of 2, but times, allow me to rewrite it. So this e to the natural log of 2 over 15 is the same as e to the natural log of 2, but multiply with 1 over 15. 1 over 15, all right? That's how I see it. That's how I see it. And so now a little more important with the algebra understanding, with our algebra, our understanding in algebra, e to the natural log of 2, and this is a product, because natural log of 2 over 5 in this power here is a product of natural log of 2 and 1 over 15. That's how I expressed that. I expressed that from this quotient into this particular product. But now I turn that into a product here for a reason, because now this entire expression is the same as e to the natural log of 2, but raised to the power 1 over 15. E to the natural log of 2 raised to the power 1 over 15. Okay, so let's have even a closer look for that inside part right here. Okay, e to the natural log of 2, but recall for yourself, natural log is the log base e. Natural log means log base e. Natural log of 2 means log base e of 2. And here I'm looking at e to natural log of 2. E raised to the power of log base 2. E raised to the power of log base e of 2. Log base e of 2. So that part, the entire expression inside of the parentheses is here really going to turn out to be just 2. According to that property we have learned back in the lecture where I showed the properties of log, then we have, anytime we have a value, a base raised to log of the same base, see, a raised to log base a of a value x, then that answer there equals x. Okay. Now at our time learning the properties, when I was giving the lecture about this property, I went really skippy because there was no direct use at that instance yet. But somewhere here and there we will keep seeing this property resurface. So every property of logarithm is important. Just because in one particular lecture, or just because in the original lecture it was not mentioned much, doesn't mean we're gonna let go of that. All right, every property I mentioned in that introduction, where all the properties of logarithms are introduced right there, every property is important to know. Okay, so particularly that property we've learned here made it possible to turn this ugly looking expression into 2. So now the inside parentheses, the part inside parentheses here now is 2. So that means it's 2 to the 1 over 15 power. And so altogether it means the 15th root of 2. Just the 15th root of 2. See how shocked that is, how shocking that is. With an ugly looking expression like this, it turns out surprisingly just 15th root of 2. 15th root of 2. So now with this scratch work showing my thought process here, and that's for the people who love algebra over here. But when it comes to this point right here, in case you don't like working directly too much with the algebra, well, we're still in algebra, but in case you don't want to go too much into all the elementary steps right there, then you can also use a calculator. All right, so here we go. This is our calculator right here. And so now I'm going to type E, okay, but raised to the power of natural log of 2, okay, and then, but that there I'm going to divide by 15. All right, and so this value right here is a 1.04729, but that is also the same. So on the board I already showed that it's really the 15th root of 2, so that means it's 2 to the power of 1 over 15. Okay, and it should be exactly the same values. The same value right here because they're the same. Okay, and so now we're firm right here, but for now I'm gonna stick with this root expression until the very final point right there. All right, so now here we go. So that means 1 plus the effective rate, or the APY right here. This is the APY as well, also known as the APY, is equal to the 15th root of 2. And now we're so ready to solve for the effective rate. So the effective rate here is just a matter of subtracting 15 root of 2. Subtracting 1 from 15 root of 2 right there. All right, so now we have our right to go with all the decimals, the crazy decimals. So really effective, the rate here equals, now let me swing back to the calculator screen right there as well. All right, so now with the calculator, we can either go with this expression or that expression, but now subtract 1. So the answer there minus 1. All right, we're going to end up with this. So this is going to be 0.04729 and a lot longer. Like that. So how about 5 decimal places? It's good enough. Okay. So the effective rate is 0.04729. All right, that's our effective rate right there. Okay, and that's how we've found it. So now, after being done, now this effective rate right here is, again, in this particular problem, it's also known as the APY, the annual percentage yield right there, because again, back to the other board where I was sketching down the information. Our default time period is in year. It's every 1 year like that is the default time period, and we extracted that clue from that piece of information where it said it was at some given annual interest rate. Okay, at some annual interest rate right there, and so we knew that we were working in default time, the period being in year. Okay, and so that's in year, so t is in year, and so that's why now this rate is the rate per year, or this is the annual percentage yield, or also the annual effective rate right there. Okay, so we can make a note of that. This is annually. All right, that's annually. Okay, so now once we're done with finding the effective rates, here comes the next question. All right, so question C right here. Find the function, okay, in the form Q of t equals Q sub 0 times 1 plus the effective rate to the t power. Okay, so find a function in the form, in this form here, that models the amount in t years or after t years. So the real situation here is that money is clear to grow continuously. That's already nailed down right there. And now we're talking about two different forms. We have previously found in part A, Q equals Q of t equals 4,000 times e to the natural log of 2 over 15t. That's the form we found of our modeling function from part A, but that was in base E. So now the difference here is that we want to come up with the same function, I mean a different expression of the function basically. We want to find a function that is in a different expression, but it models the exact same thing. It still models Q right there, the amount in t years. Okay, but in the base, that base being 1 plus the effective rate. That's what it is. Okay, so Q sub 0 is still going to be the same, 4,000. All right, so now in that way, it's going to be as easy as Q of t equals 4,000 times 1 plus, and now I calculated that effective rate in the previous question to be in 5 decimals about 0.04729. So 1 plus 0.04729, and now raised to the power t. That's our function. Okay, and then we can make it shorter a little bit by rewriting this 1 plus 0.04729 here as 4,000. Okay, times 1.04729 to the t. So now we are in a completely different expression, but these are the two different forms. So this forms here, remember that in the discussion prior to getting to this example, then I was saying that this particular form is useful for when, think about when you're sitting home and you know your money is growing continuously already. Okay? But if you want to monitor, or if you want to watch your money growing in every year like that, then this model is good. It gives you the exact number every year. Rather than if you are using this, okay, then you're going to have to deal with base E right there. Okay, you're going to work with base E, and the worst case is that some basic calculators in these days still do not offer base E calculation. Whereas with this, you can just type in, if you want to find out how much money you have produced in year 20, in 20 years, okay? In 20 years, then it's going to be 1.04729. These are all available in the calculator. 1.04729 and raised to the power of 20 and then multiply with 4,000. It gives that amount that you can predict in 20 years, that you can predict quite precisely. All right, and that's the whole intention of this example. It is given now to emphasize what we have just learned about that relationship between, first of all, it's that understanding that we make some clear distinguish between the effective rates and the nominal rates. And then there's a relationship between effective rates and the nominal rates. That relationship was 1 plus effective rate that equals e to the k, where k is the nominal rate right here. This is something to nail down right there. Okay, and admittedly we've only been through with 2 examples, but you will keep seeing this a lot more often. All right.